Higher Physics Notes, Unit 2, Section 5, Interference and Diffraction, Part 2. So we're going to look in this section at diffraction gratings. Now you'll know that in the Young's slits experiment, we had two slits like that to let our light through. But in a diffraction grating, we have multiple slits. So a grating would be represented by this. You can effectively think of the grating as being many pairs of slits set symmetrically about the centre. The advantage of gratings are twofold. You get more light through, so a brighter interference pattern, and the second one is you get a sharper fringes. We don't need to go into the background to that. So a typical setup then would be that you would use a laser to produce a monochromatic beam of light, like so. And the monochromatic beam of light would hit the grating. Now, of course, the grating is not to scale here. Don't want to do it in that colour. Obviously, the grating would be much smaller than this, and the gap size would be considerably smaller. Anyway, what happens is that you get an interference pattern very similar indeed to the two-slit interference pattern. There's my straight through position there. So if this were your screen, then you would get your interference fringes, central maximum, first order on each side, second order on each side, etc. M equals 0, M equals 1, M equals 2, just as before. And if we show the angle of deviation theta, let's just take the second order fringe. This would be the deviation angle theta. Well, it turns out that there is an equation called the grating equation, which says that m lambda equals d sine theta. That is the grating equation, and will be on your list. So what do all these things mean? Well, theta is the deviation angle. In degrees, that's the angle you can see in the diagram. Lambda, of course, is the wavelength of the light being used, and this, of course, m is the fringe order number. Now, what about d, small d? Well, d is the slit separation. Let's just have a wee look at that below. So if we imagine that we have our diffraction grating, okay, well, two things. Don't get confused between the slit separation and the slit width. So the slit width is the actual width of the slit, which needs to be less than or equal to a wavelength. Okay. So that's sometimes called W, the slit width, and it's always less than or equal to lambda. Now that's not in the equation, but I'm pointing it out to you so that you don't get confused. Okay, so W is the slit width. Has to be less than or equal to lambda to get diffraction at each of those individual slits. Now the slit separation, on the other hand, is the distance between two adjacent slits. So from the centre of one slit to the centre of the next. And hopefully you can see the distinction. And that's called D, slit separation. So, the D in the equation m lambda is d sine theta. That D is slit. Let's do an example so that you can see how it works in practice. So, a diffraction grating has 300 lines, and by lines we mean slits. They're often called lines per millimetre, and produces an interference pattern the second order maximum is at an angle of 19 degrees. So that's the theta that you can see in that diagram, 19 degrees in this case. Calculate the wavelength of the light. Now, it's quite common in most of these problems to have to get D sorted first, okay? So you're told that we have 300 lines per millimetre. So the first thing you've got to do is to get that into how many lines per metre. Well, 300 lines per millimetre. There are 1,000 millimetres in a metre, so that's 300,000 lines per metre. But be careful, that is not D. D is the separation of the lines or slits. So to get D, you basically take 1 over that. And when you work that out on your calculator, 3 significant figures, you'll find you've got 3.33 times 10 to the minus 6 metres as your slit separation. So that's D sorted. So we can now invoke our equation for a maximum. Should of course flag up that this equation applies for maxima. So we know it's the second order, so m is 2, lambdas are unknown. We've just worked out D, 3.33 times 10 to the minus 6. The deviation angle is 19 degrees, so it's the sine of 19. And when you rearrange that, you'll get lambda is 3.33 times 10 to the minus 6 times the sine of 19 divided by 2. Don't do any rounding until the final line of reasoning, and you'll get that the wavelength is 5.4 times 10 to the minus 7 metres. So that's about 540 nanometres, which places it in this sort of middle of this visible spectrum, so it's going to be green in this particular case. Now a little bit of geometry of this situation. So we've basically got, from the centre of the grating, a line going to the screen, and so that would be the m equals 0 position. And we can draw a line up to our m equals 2 or whatever m is involved, and that creates a triangle, like so. Just compare that with the experimental setup. You can see the triangle emerging there. We call this distance d, and we call this distance x. So if that's our deviation angle, theta, there you can see it. Well, we can use our trigonometry to say that tan theta, which is opposite over adjacent, would be x over d. And sometimes in problems, to get theta, you will need to do a calculation like that. Another useful thing to remember is what's called the small angle approximation. Obviously tan theta is not in our equation, but the small angle approximation tells us that if theta is very small, then tan theta is approximately the same as sine theta. And that can be quite useful when we're looking for sine theta, because it's in our equation. We'll ignore that interruption. So that can be quite a useful little bit of geometry which you can use when working on these problems. Sometimes in order to get sine theta, you need to use the x and the d values to get tan theta, and that can give you theta, I suppose, but if the angle is very small, then tan theta is pretty much the same as sine theta. By small, we mean typically 1 degree or less. So if you take your calculator and put in tan of 1 degree, and then do the same for the sine of 1 degree, you'll see you get pretty much the same number. So 1 degree or less, and tan theta and sine theta are pretty much the same thing. And just to finish off this section, a little look at the spectrometer. This is the device used to make accurate measurements with diffraction gratings. They have finely engineered turntables with an angular scale on them, which allows theta to be measured quite accurately. So you would have your light source from a lamp, probably shielded, could be a laser of course as well, and your light would come out like that. It would then pass through a slit and go along what's called a collimator, which is just a tube basically. And the reason for the collimator is that it ensures that what emerges from the collimator is a nice narrow parallel beam. Anything that's not travelling in the right direction would be absorbed by the sides of the collimator. You then have an angular turntable like that, and if I show the sort of straight through position, and our grating would be placed here. And in order to view the fringes, you have a small telescope so that the observer's eye is in there, and the beam would proceed, and depending on which order you were looking at, you would see the maximum fringes. And what's done in practice is that you would move your telescope round so that you would measure theta here and here. So if we call that theta 1 and theta 2, the angle of deviation theta itself would be theta 1 plus theta 2 divided by 2. This is an experimental technique which is useful for more accurate measurements of theta, because by measuring the angle between the two extremes there, measuring theta 1 plus theta 2 effectively, you're measuring a bigger angle, therefore your percentage uncertainty in the reading of the scale is smaller. So it's a more accurate way of measuring theta, and that can then be plugged into the grating equation. Some wavelengths that you should memorize of light. These should be known by heart. Are red, where the wavelength is approximately 700 nanometers, which is 7 times 10 to the minus 7 meters. Green, in the middle of the spectrum, So its lambda is typically taken as about 520 nanometers or thereabouts. That's 5.2 times 10 to the minus 7 meters. And then down at the blue end, shorter wavelength end, of course, we're talking about 460 nanometers, which is about 4.6 times 10 to the minus 7 meters. Okay, so you should know those approximately, although you can always access wavelengths of these colours by looking up the data page where various emission line colours are given, so you can get an approximation to the wavelengths from there. And the last thing on the dispersion of white light. So if you have a grating and you shine white light at it, then what's going to happen? Well, you will find that you always have a white fringe at the central maximum. That is always white. The reason for that is that if you think of symmetrical pairs of slits about that central position in the grating shown, then the path difference is 0 between those pairs of slits for all wavelengths. So they all arrive in phase together and you always get white there. However, if you go to, let's say, the first order maximum, then you'll find that you've got your red end of the spectrum further out than the violet end, and of course green would be in the middle. And you'll get the same thing happening down at the lower position. Notice that red, having the biggest wavelength, is diffracted most. Violet, having the smallest wavelength, is diffracted least. Green, of course, is in the middle. So that would be your m equals 1 first order maximum on each side. So in fact, when you have white light on a grating, instant on a grating, the central maximum will always be white, but all the other fringes, maxima, will be little visible spectra with red diffracted most. Now you can see why red would be diffracted most if we look at our equation. M lambda is d sine theta. So if we think of our diffraction angle theta, or sine theta at least, that's going to be m lambda over d. Now if we identify all the constants here, let's say we choose first order, so m is fixed. D for any given grating will be fixed. So you can see in rough notes here that if lambda is big, then sine theta will be big. In other words, the greatest theta, the greatest sine theta, will be for the larger wavelength. So larger wavelength means larger theta. And that's why the red light is diffracted more than the violet light. You can see that if I just sketch the angles. So there would be the angle of deviation for red. and here would be the angle of deviation for violet, slightly less. Okay, so there's theta for violet, and there's theta for red. Bigger deviation for bigger wavelength. And just before I stop this note, compare that with the kind of dispersion you get with refraction with a prism. When you send in white light to a prism, it's the red light is actually refracted least, and the violet light is refracted most, with green obviously in the middle. So, whilst the long wavelength of red is refracted least, that longer wavelength of red is diffracted most. Just to finish off, a wee note on the central maximum being white. Basically, this is because path difference for all wavelengths is 0. So all colors overlap in phase to give you a white maximum. It comes up in exams, that question, so it's actually worth just even memorizing that, should it ever come up. And just before we end, a couple of applications of interference. You don't really see much in everyday life, but behind the scenes there are a number of useful applications. One is in producing holograms. Hologram, of course, is a 3D representation using light of an object. It's also used in engineering in stress analysis to determine the forces on objects and whether they might be at excessive stress in structures. And it's used in research in interferometers. Obviously, doing experiments with light, measuring wavelengths of light in astronomy, for example. And that brings us to the end of 2.5, Interference and Diffraction, Part 2.